Welcome to this talk about an improved approximation guarantee for the price-collecting traveling salesperson problem, which is joint work with Nägele, and we are both from the University of Bonn. Let me first start with a formal problem description. The price-collecting traveling salesperson problem, or short Price-Collecting TSP, is the natural generalization of the metric traveling salesperson problem. So the metric TSP, probably most of you know this problem. We have given a complete graph G and a metric cost function C. And there the task is to find a cycle that visits each vertex exactly once and has minimum total cost. And in the price collecting version of this problem, we have additionally given some root vertex R and penalties for all vertices except the root, which are shown in the example on the right hand side by the red colors inside the vertices. And the task is that we want to find a cycle that covers at least the root and minimizes the cost of the cycle, which we denote by the connection cost, and the penalties for all vertices which are not covered by the cycle. So a solution to this problem could look like this. And we see there are two vertices which are not contained in the cycle, so we have to pay the penalty for these vertices. So this problem has obvious applications in logistics, and as already mentioned, it generalizes the metric TSP. And indeed, if we choose the penalties to be very high, then if we want to find a good solution for this problem, we have to find a solution that covers all the vertices. So this also concludes that this problem is NP hard and even APX hard, which is why one main focus of research lies in finding good approximation algorithms for this problem. So let me shortly recap what's already known about the approximability of this problem. It more or less started with a 2.5 approximation 30 years ago, and using some threshold rounding approach, and in a few minutes I will tell you in a bit more detail how this threshold rounding approach works, because we also use some kind of threshold rounding in our approach. Okay. 2 years later, Gomans and Williamson improved approximation guarantee to 2 using some primal dual algorithm. In 2009, the approximation ratio was improved even further to 1.98. And in the same year, Gomans observed that if one combines the threshold rounding algorithm and the primal dual algorithm, one even gets a 1.91 approximation. And our contribution is that we now close further the gap between the approximability of price collecting TSP and metric TSP by providing a 1.774 approximation. And now let me show you a natural LP relaxation for this problem, because our algorithm will build up on this LP relaxation. And here we have given x variables for the edges and y variables for the vertices. And these y variables tell us to which extent some vertex is connected to the root. So we also call these y variables the vertex connectivities. And indeed, we have these cut constraints here, which tell us that the x value of delta of s for each set s must be at least 2 times the maximum vertex connectivity among all vertices in S, where delta of s denotes the edges adjacent to S. Okay. And if some vertex connectivity is equal to 1, then we do not have to pay the penalty at all. But if some vertex connectivity is 0, then we have to pay the full penalty. And the solution to this LP relaxation could look like this, here in the example on the right hand side. So we have some vertices with vertex connectivity 1, so they are fully connected to the root, and then some other fractional vertex connectivities, which are only partially connected to the root. And I already mentioned that I would like to recap the threshold rounding, the classical threshold rounding algorithm from 1993 by Bienstock, Gomans, Simchilevi, and Williamson. And the algorithm is very simple. We first of all, we start with some threshold gamma, and we now define the core set to be V gamma to be all the vertices for which the vertex connectivity is at least the threshold. So if we, for example, choose this threshold to be 3/5, then the core set would consist of all green highlighted vertices here. And the algorithm is now very simple. We just apply a TSP algorithm on this core set, which then results in a cycle containing exactly these vertices. And of course, if we want to get a good approximation guarantee, we should use some TSP algorithms, which as well guarantees us some good approximation guarantee for metric TSP. And for this, let me shortly recap Christofides' algorithm, which gives us 3/2 approximation for metric TSP. There has been some slight improvement by Kalin Klein Garan recently, but since improvement is only very small, we will just use Christofides' algorithm here because it makes some things a little bit simpler. Okay, Christofides' algorithm more or less consists of 3 steps. So in step 1, we take a shortest spanning tree on our vertices, and we call the TSP algorithm only on our core set, so we only want to span this core set here. Then we add the shortest out of T join, which means that we want to find the shortest subgraph, such that if we add the subgraph to our tree, such that afterwards each vertex has even degree, which is why this step is also called parity correction in literature. And then the last step, we just take some Eulerian tour on the resulting graph and shortcut, so that each vertex is visited exactly once, so that we get a cycle in the end. And this shortcut step also does not increase the cost because of the triangle inequality that we have. Okay. So let us shortly analyze this algorithm. So there is some very well-known LP relaxation for metric TSP, which is Held-Carp relaxation, which is very similar to the LP relaxation for Prize-Collecting TSP that we have already seen. So we have these cut constraints that we want that each cut value must be at least 2, and also this degree constraint that the degree of each vertex must also be exactly 2. And Woolsey's analysis of Christofides' algorithms shows that the cost of the tree can be bounded by the cost of the LP solution, and the cost of the join can be bounded by 1/2 times the cost of the LP solution. So in the end, we get a cycle that costs at most 3/2 times the optimum LP value. And this we now use to analyze the threshold rounding algorithm, which we do by linking the Prize-Collecting TSP LP and the Held-Carp relaxation for metric TSP. So we start with a feasible solution for the Prize-Collecting TSP LP, and what we now do is that we scale up the X part of the solution by a factor of 1/gamma, and this also boosts up our vertex connectivity, so that after the scaling, each vertex in our core set has a vertex connectivity of 1, so it's now fully connected to the root. And now we use some well-known tool, namely splitting off, which is already known since the 70s, to generate a solution in the Held-Carp polytope on our core set, starting at this solution here. So what we exactly do is that we consider some vertex below the threshold, so for example this one here, and now splitting off tells us that there are always 2 adjacent edges, such that we can decrease the weight on these edges by some amount and increase the weight on the edge linking the other 2 endpoints of these 2 edges by the same amount, such that all vertex connectivities maintain unchanged. So more precisely, splitting off tells us that we can find such a splitting off operation such that for all vertices u and v, which are not equal to the vertex where we applied the splitting off operation at, the size of the minimum uv cut is unchanged. Okay. And if we do this iteratively, then indeed we end up in a feasible point z in the Held-Carp polytope on our core set. And now we can just use Woolsey's analysis of Christofides' algorithm that we have discussed a minute ago to see that we can get a cycle of total length at most 3/2 times the cost of z. which is at most 3 over 2 times gamma times the cost of x, because splitting off does not increase the cost of our fractional solution, again because of the triangle inequality. Okay. So this is the bound that we get in the cost on the cycle. We still have to analyze the penalties that we have to pay, but this is pretty easy because the penalties that we have to pay are exactly those for which the vertex connectivity is below the threshold. And since it's below the threshold, we can bound this, we can introduce this factor here of 1 minus the vertex connectivity of 1 minus gamma, which this factor is at least 1. So we get the factor of 1 over 1 minus gamma times the cost that we have to pay in the objective of the LP relaxation. So we have these two factors that we want to balance by making a good choice of our threshold, and if we choose the threshold to be 3 over 5, we get a 5/2 approximation. Okay, so this is this very well known 5/2 approximation, which is already 30 years old. And now in the second part of the talk, I will tell you how we improve upon the so far best known approximation guarantee. And what we do is that we exploit one major weakness of the thresholding approach, because when we transform our price-collecting TSP LP solution X to this point Z in the Held-K polytope on our core set, we do this by using splitting off, and this way we completely lose the coverage of the vertices below the threshold. So here again in this picture here you can see an example of one of these splitting off operations, and on the left hand side you can see the price-collecting TSP LP solution X, where we only have to pay the penalty for this vertex by a factor of 0.3. And now we apply splitting off to generate this point in the Held-K polytope, and afterwards this vertex isn't connected at all to the root anymore. Okay, so here we have to pay the full penalty for this vertex. But in the analysis of threshold bounding, we bounded the cost of this point in the Held-K polytope by the cost of x. So in the analysis, we did not exploit that technically it would be possible that by doing the splitting off, we could save something in the cost, because we know that if we apply splitting off, the cost cannot be higher because of the triangle inequality. But in fact, it could be the case that we save something, but this is something that we do not exploit in the analysis. And it's very difficult to exploit this, but what we instead can do is that if we decide that this edge here should be part of our cycle in the end, then in some cases we would like to undo the splitting off so that we again have some coverage of this vertex here, so that afterwards then this vertex, in some cases at least, is part of our cycle. Okay, so we want to unpack these splitting off operations, but what we like to have is that we would like to keep the bound on the cost of the cycle that we paid in the classical analysis of the threshold rounding algorithm, which was 3 over 2 times gamma times the cost of x. Okay, so we would like to keep this bound on the cycle cost while improving the bound on the penalty. And this is easiest by using some randomized approach. So we would like to keep this bound on the cost of the cycle in expectation. And what we would like to get is that for each vertex which is not in our core set, that this is covered by the output cycle with some certain probability. Okay. And this we achieve as follows. So what we do is that we open the black box of Christofides' algorithm. Again, this was consisting of these three steps here on the left hand side. And the first step was taking the shortest spanning tree. And we replace the step by first sampling a tree with marginals approximately to Z, which was the point in the Held-K polytope on our core set. And for the sampled edges, we now undo the splitting off operations. If we do this in expectation, we still keep the bound of 1 over gamma times the cost of x on the cost of this what we call extended tree, which isn't a tree anymore. I mean, if we look at some examples, so the spanning tree that we sampled could look like this. And now we undo the splitting off operations so that we now get some, this now results in these walks starting and ending in our core set, and in between we visit some vertices. And for these vertices, these are now covered by our trees, so we do not have to pay we will not have to pay the penalties for these vertices. Okay. Now again we apply parity correction, and what's nice is that we observe that the odd degree vertices are still a subset of our core set. So the cost of this parity correction will keep the same. So an expectation we have to pay 1/2 times gamma times the cost of x. Okay, and then again we shortcut, get the cycle, and we observe that the expected cost of the cycle, for this we get a bound that is exactly the same as in the classical analysis of threshold rounding, but we have included some of the vertices below the threshold. So we have improved the penalty that we have to pay. Okay, but what penalty do we have to pay? So this we still need to analyze. And for this, we consider some vertex which is not in our core set, and we now want to bound the probability that this vertex is not covered by the extended tree, which resulted from sampling the spanning tree on our core set and undoing the splitting off operations. But if we undo the splitting off operation, this we have already seen on the previous slide, this results in walks starting and ending in our core set and visiting some vertices in between. And there is some one-to-one correspondence between these walks and the edges in the point of the held car polytope on our core set. Okay, so, and that this vertex is not covered by the extended tree equals the probability that no of these walks going through this vertex V, that all of these walks are not covered, not sampled. Okay. Now we exploit a very nice property of many random spanning tree sampling procedures, that is that the event that two edges are not sampled is negative correlated. So we can bound this by this product going over all these walks, the probability that this walk is not sampled. But the probability that this walk is sampled was chosen in a way that this is approximately the weight of the walk. So we get that this is approximately this for this example here on the left hand side. And if we assume that each of these walks pass through our vertex V1, we can link these walk weights with our vertex connectivity YV. So then we get this upper bound on this probability of e to the minus YV over gamma. Okay, so now we have some very nice bound on the probability that some vertex is not covered. And here we have some improvement. Okay, but we are not done yet, because this assumption here must not always be true. As we can see here in the picture in this example, so we have this is just not a full instance, but a part of an instance with two vertices U and W with a vertex connectivity of 1, and all other vertices, which you can see have a vertex connectivity of 1/2. And if we would have this decomposition into walks, which results from undoing the splitting off operations, this decomposition could look like this. And what we see here is that we have some cycle inside one of these walks. And now we have some vertex V down here, for which the total weight of the walks that go through V is only 1/4, because there's only one walk going through this vertex. But the vertex connectivity was 1/2, so this does not match anymore. But we can fix this by decomposing our LP solution into walks, but into trees, which are anchored in exactly two vertices of our core set, as we can see here in the example now. And for those anchored trees, we now have the property that the vertex connectivities are exactly equal to the total tree weight, and this is true for each vertex. But now we could have a problem with the parity correction, because we see for the vertex V here we have odd degree, and this is not good, because then it might be the case that we then have to pay more on the parity correction step. And we avoid this by using not these trees for building our solution, but instead using two kind of walks. As I said, these trees are anchored in exactly 2 points in our walk set, so this means that we have some what we call a backbone path between these two anchor points that you can see here on the left hand side. And the other part of the tree we call the limbs, and we now have the possibility that we delete the limbs here on the left hand side, or we double the limbs. And in both cases we now have even degree on all vertices which are not in our core set, which is what we wanted to have, so that the parity correction will not be more expensive than previously. And we choose these two possibilities with some certain probabilities, such that the cost bound will stay the same on the cycle cost. And now in the end we get that the probability that some vertex is not covered is the same that we've seen before, but now we have this additional factor of 3/4. So we lose here a little bit, but not too much. Okay, so now if we wrap things up, this results in the following theorem, and this theorem is already de-randomized. So until now we only have spoken about a randomized approach, but one can use very well-known and common de-randomization techniques to get the following theorem. So if we have given some LP solution of our price-collecting TSP relaxation and some threshold gamma, we can get in polynomial time a cycle such that the cost of the cycle plus the penalties for the vertices which are not covered by the cycle can be bounded by 3/2 times gamma times the x cost of our LP solution. And this is again the exact same factor as that we already had in the classical analysis of threshold rounding, plus now for each vertex with vertex connectivity below the threshold, we have to pay the penalty, but not always anymore, but only with this probability here. And this is where we improve things. And if we now choose our threshold gamma with respect to some specific probability distribution that you can see here on the right hand side, we get 1.774 approximation. And also the choice of the threshold gamma can be de-randomized by just trying all vertex connectivities that occur in our LP solution as threshold and just take the best solution that we computed. Okay, this also gives an upper bound on the integrality gap of the natural LP relaxation. Okay, so now let me finish this talk with two open questions. So we have seen we have this upper bound on the integrality gap of 1.774. Another question is, of course, what's the best known lower bound on the integrality gap? And in fact, there's nothing better known than a lower bound of 4/3, which is already the best known lower bound for metric TSP. So there's, and of course, a lower bound for metric TSP also implies the same lower bound for price-collecting TSP. So there's just nothing better known for this generalized problem. Okay. And of course, another question is also whether we can maybe further close the gap between the approximability of price-collecting TSP and metric TSP. Thanks for your attention.